Suppose you have a triangle, an acute angle triangle, such that alpha, beta, and gamma are all less than 90 degrees each, and then you drop the altitude from this vertex to this side of the triangle. Then the length of this small segment here plus the length of this small segment here equals, can you guess it? You guessed it, the length of this side of the triangle. But why is this so important? Isn't that too obvious to be mentioned? Well, it's really important actually. In the next couple of videos, I'm going to show that literally all the trigonometric formulas follow from the simple fact about the triangle, that this length plus this length equals this length. By the law of sines, we know that this side equals 2 times r times sine of alpha, where r is the circumradius of the triangle, the radius of its circumcircle, and this side is 2r times sine of beta. Then, because this here is a right-angled triangle with hypotenuse 2r sine of beta and angle alpha here, then we know that this side equals this side times cosine of alpha. And so this side equals 2r sine of beta times cosine of alpha. Similarly, for this right-angled triangle with hypotenuse 2r sine of alpha and angle beta here, we know that this side equals 2r sine of alpha times the cosine of beta. So now if we take the sum of these two lengths, we're going to get the length of this side of the triangle, which by the law of sines is 2 times r times the sine of gamma. And that's how we get this equality. And now we can cancel out the 2r, and we can substitute gamma with 180 minus alpha minus beta. We got that sine of beta cosine of alpha plus sine of alpha cosine of beta equals sine of 180 minus alpha minus beta. But we know that sine of 180 minus alpha minus beta equals sine of alpha plus beta, because the sum of 180 minus alpha minus beta and alpha plus beta is 180 degrees. And this is how we get the following trigonometric formula. Sine of alpha plus beta equals sine of alpha cosine of beta plus cosine of alpha sine of beta. Now let's show that this formula is true not only for acute angles alpha and beta, but also, for example, if beta is obtuse. Suppose this is our triangle, where angle beta is obtuse, then this is the altitude in the triangle. We're going to assume that this triangle has a circumradius of 1/2, and therefore, from the law of sines, this side is sine of beta, because 2 times r is just 1. Then, from this right-angled triangle with hypotenuse sine of alpha and angle here 180 minus beta, we know that this side is sine of alpha times the cosine of 180 minus beta. And from this right-angled triangle where the hypotenuse is sine of beta and this angle is alpha, we know that this side is sine of beta times the cosine of alpha. And now we get that sine of gamma equals sine of beta cosine of alpha minus sine of alpha cosine of 180 minus beta, which is written here. But sine of gamma equals sine of 180 minus alpha minus beta, which equals sine of alpha plus beta. And finally, we know that cosine of 180 minus beta equals minus cosine of beta. So this minus is going to become plus, and this cosine of 180 minus beta is going to become cosine of beta. And then sine of alpha plus beta equals sine of beta cosine of alpha plus sine of alpha cosine of beta, which is exactly the same formula as here, but right now beta is an obtuse angle. In fact, this formula is true for all angles alpha and beta, no matter their size. They can be negative angles, they can be larger than 360 degrees, whatever. This formula here is always true. Here's the optional problem. We have a triangle. This is its incircle. These 3 points are the tangency points of the incircle with the sides of the triangle. Then we connected these 2 tangency points, and we constructed the perpendicular at this tangency point to this line, which intersects this segment here at this point. And then we took this to be the midpoint of this side. We should prove that this point, and this point lie on a straight line. And here's the solution. I'm going to denote this segment by x and this segment by y, and also this angle by alpha and this angle by beta. Since this angle here is 90 degrees, we know that this angle is 90 minus alpha. And by the alternate segments theorem, we know that if this angle is 90 minus alpha, then it corresponds to this arc in the circle, and so it equals this angle 90 minus alpha. Now, since the sum of the angles in this triangle is 180 degrees, and we have 90 minus alpha here and alpha plus beta here, it follows that this angle is 90 minus beta. Also, we know that this length equals this length, since this and this are tangent lines to this circle from this point. Then, this triangle is isosceles, therefore, this angle equals 90 minus alpha. And now from the sum of the angles in this triangle, it follows that this angle is 2 times alpha. Similarly, if this angle is beta, then this angle must be 2 times beta. Let's apply the law of sines for this triangle and this triangle. We get that x divided by y equals sine of alpha divided by sine of beta times sine of 90 minus alpha divided by sine of 90 minus beta, which is written here. We know that sine of 90 minus alpha equals cosine of alpha, and sine of 90 minus beta equals cosine of beta, and so we can rewrite this expression like that. We know that sine of alpha plus beta equals sine of alpha cosine of beta plus cosine alpha sine of beta, and therefore, if we substitute beta for alpha, we get that sine of 2 times alpha, alpha plus alpha, equals sine of alpha cosine alpha plus cosine alpha sine alpha, which is 2 times sine of alpha cosine of alpha. Therefore, sine of 2 times alpha equals 2 sine alpha cosine alpha. And so we can substitute this sine alpha cosine alpha with sine of 2 alpha divided by 2, and we can substitute this sine beta cosine beta with sine of 2 beta divided by 2. But the 2's are going to cancel out, and therefore this ratio equals the ratio of sine of 2 times alpha divided by sine of 2 times beta. So we get this. Now let's intersect the median, the red line, and this line here at this point, such that this distance is x prime and this distance is y prime. It's clear that if we prove that x equals x prime or y equals y prime, then the statement would follow, because this point would also be the intersection point of the perpendicular from this point to this line and this line here. Let's call this angle delta and this angle psi. Also, let the length of this segment be m, and the length of this segment is also m, because these are tangent lines to this circle from this point, then this equals this. Also, we know that this point is the midpoint of this side of the triangle, so let's call this segment n, then this segment is also n. Now let's apply the law of sines for this triangle and this triangle. We get that x prime divided by y prime equals sine of delta divided by sine of psi times m divided by m, which is written here. Now m divided by m is just 1, so we can ignore it. And now let's apply the law of sines for this triangle and this triangle. We get that sine of delta divided by sine of psi equals sine of 2 alpha divided by sine of 2 beta times n divided by n, which is written here. But now n divided by n is just 1, so we can ignore it. So x prime divided by y prime equals sine of 2 alpha divided by sine of 2 beta. But that's exactly what we needed to prove, because x divided by y is sine of 2 alpha divided by sine of 2 beta. So x prime divided by y prime equals x divided by y. From here, it easily follows that x equals x prime and y equals y prime, which means that the median intersects this line at the same point at which the perpendicular from this point intersects that same line. And so problem is solved.